Hi, my name is Rebecca Lindow, and this is my EMU GRC presentation on the evaluation of parameters affecting antibiotic production in soil microbes. Currently, the CDC estimates that about 35,000 people in the US alone die from antibiotic-resistant infections, and they estimate this number to increase by about tenfold by the year 2050. And we can see in Africa and Asia, this number is in the millions, and that's just kind of showing just how crazy high these numbers are. However, as antibiotic resistance is rising, we're seeing a decrease in antibiotic production. And so we see in the 80s, we had almost 16 brand new antibiotics released. And well, this is kind of old, but in 2003 to 7, we see that there were only about 5. And so what this is showing is just that it's so expensive for pharmaceutical companies to get into antibiotic research that they just kind of don't. And so a lot of this research just kind of depends on universities. And so opportunely, Eastern Michigan, in the Price Lab, came up with the modified crowded plate technique. So what they're doing here is they're taking some sort of pathogen and they're smearing it all over the plate. They have soil microbes, so most of our antibiotics come from soil microbes, and so we're just going to keep kind of going after that. We combine those together, we get lots of competition, and that's how we get some halos, which would be indicative of antibiotic production. And so what we see right here, we have this little brown guy in the middle, and around him is a clearing, and that's indicating an antibiotic producer. So what we want to do here is we want to just kind of improve the recovery of antibiotic producers. And so we have 3 means of doing this. We want to see if the use of oxotrophic pathogens increases antibiotic production. We want to see if soil pathogens can be used in lieu of a human pathogen. And we also want to see if mixed fermentations improve antibiotic yield. So to tackle that first question, we should probably define what an oxotrophic pathogen is. So an oxotrophic pathogen, it requires supplemental media, so it's a mutant that lost the alanine racemase in this scenario. So what that means is L-alanine is in the environment, and it's what we use, it's just kind of what's there. Bacteria need D-alanine in order to make their cell wall, and so what they do is they have an alanine racemase, which is just an enzyme that converts L-alanine to D-alanine. However, when we make these mutants, we get rid of that alanine racemase, means there's no more D-alanine, which means there's no cell wall, unless we supply it to them. So when we supply it, the pathogen can grow. So that pathogen would be that smear that we saw in the previous picture. So the pathogen can grow, that's great. And then we can put our soil on top of that, great. We find antibiotic producers, bingo, that's what we want. But we don't care about the pathogen after we find a producer. All we want is the producer. So when you take away that D-alanine, you just have minimal media and you just find the producer. You no longer have the pathogen. So it's a really easy way to isolate our antibiotic producers so we can do further testing on them. And so one thing we did to test for this was we used soil bacteria on either a wild type pathogen or an oxotroph pathogen. So here on the left, we have our wild type pathogen. And then if we zoom in, there's a producer right there. So you can see the margins of the bacteria and you can see the halo right around it. It's kind of small. Here we have our oxotrophic pathogen and you can see a lot of halos that are pretty obvious. And if we zoom in on one, we see that the halo is pretty large. So the main difference we saw between oxotrophic and wild type pathogens is that we saw more and bigger halos on the oxotrophic pathogen. So that was pretty cool. So from there, we have even more antibiotic producers that we're going to be able to isolate, which is pretty good. So our next question was if we could use a soil pathogen instead of a human pathogen. So the reason for this is there's unpublished data in the Price Lab that suggests there might be some sort of correlation. But when I tested this here, we can look at our graph and see that on the y-axis, it's the number of antibiotic producers, and on the x-axis, we have whether it's a soil pathogen, a human pathogen, or a soil and human pathogen. So it killed both. And so basically what this graph is showing is that we had the same bacteria kill soil pathogen, great. If it killed a human pathogen, or if it killed both the soil and the human pathogen. And so what we see is there's only about a 50-50% chance of getting a microbe that will kill both the soil and human pathogen, which is what we were looking for. So we got to look a little bit further into that. So then we looked at our mixed fermentation. So we wanted to see if maybe there's more interactions with these fermentations and we're able to get more antibiotic production. So pure cultures are the kind of the gold standard. It's what most people use and have used. And so the way you do that is you just have one single microbe and you grow that up, you extract the secondary metabolites, you plate them. And what we saw against staph in this plate is that only 80 and 83 produced anything. So that's okay. It's not great numbers, but there's something. Under co-culture, however, we now see what we're doing is we're taking a mixture of 3 microbes. And so the ones we chose were just the non-producers from the pure cultures, and we plated those together. And so in the instance of G, what we're seeing is 75, 79, and 82 were all mixed together. And then we got G, and they're now producing some sort of secondary metabolite. H, I, and J were the same thing. So they were also other mixtures of microbes and that weren't producing before, and now they're producing something. So the reason for that is that there's probably some sort of induction of some other pathway. And so mixed fermentations basically just allow for more complex and lots of competition and other interactions to occur that lead to some other metabolic pathway, which could potentially lead to a secondary metabolite, which is pretty nifty. So that leads us to our final questions from before. So the auxotrophic pathogen, we did see an increase in antibiotic production. We even saw that the halos were larger. We also saw that in this scenario, soil pathogens may not be able to be used in lieu of human pathogens, but we can always check more in on that later. And we also saw that mixed fermentations improved antibiotic yield when we used non-producing pure cultures and mixed them together. So that was pretty cool. So our future directions here, we want to keep optimizing antibiotic production, and the way we want to do that is we want to characterize those liquid extracts. So those plates we just showed you, whether they were pure co-culture, we want to see what was produced. We also want to construct a MRSA auxotroph. So if we can't use a soil pathogen in lieu of a human pathogen, then we probably should make it a safer and really easy to work with pathogen. So that's the idea with that. And then we want to continue making classroom safety a priority and making more tools. And so a lot of the work that is done in this lab, in the Price lab, is actually used in a introductory undergraduate lab. And so as long as we can make that really safe for them and we can keep making tools for them, so it's really easy for them to find antibiotic producers that we can use upstairs in the Price lab, then that's good for everybody around. So, and that's my research. Thank you.